Bon, bonjour à tout le monde. Alors, je vais parler en anglais parce qu'on a des gens quand même qui parlent principalement que l'anglais, donc je vais basculer en anglais. Et j'avais prévu des transparents d'ailleurs en anglais en conséquence. Alors, comme l'a bien dit Jean-Philippe Lagrange il y a quelques instants, on est une des 10 thématiques phares de l'Institut Mines-Télécom. Et je vais présenter donc cette partie des thématiques phares. Et, okay, welcome to this colloquium on future networks and services. So I'm switching to English and describe basically the activities that are ongoing at the Institut Mines-Télécom in many of the education and research centers of Institut Mines-Télécom. You have basically on the next slide basically the aim of the thematic area networks and IoT, where our goal is to basically develop major new projects, nurture a dynamic community that can really cooperate and foster collaboration across these education centers. They are distributed and located across France, and we basically have Télécom Paris, IMT Réseaux here, Télécom SudParis in the Paris area, 30 kilometers south of Paris, and then Télécom Paris has Institut Réseaux also associated at Sophia Antipolis, and then we have IMT Atlantique and IMT and then we have Mines de Saint-Étienne, who are basically represented in this activity and contributing actively to the research that we are conducting in this area. Let me just check why I have... I don't know why what I see here and what I see on the PC are totally different. When I move on the PC, actually I don't see. Okay, never mind. Everything I prepared is down the hill. Okay, so basically what are we working on? The main research areas that we address are really covering all facets of future networks and services. And we have wireless communication at large and IoT as the scope. And we have a rather full span coverage of the area and the topics, starting from the physical layer to the applications, looking at architecture, protocols, services, applications as well, and also all segments of networks end-to-end, from devices to the cloud. Now, if we want to cluster a little bit what we do in the thematic area and in future network and services, then we would cluster that maybe into four main course research clustering areas: communications and connectivity, which is really basically radio access and access, network services seen as distributed systems, IoT and embedded systems, and then the physical layer with the electronics and the hardware part. When we look at applications, application areas and verticals, then we would cover many verticals and sectors: the industry, the energy, the health, transportation, and then all the way to public safety. And we have underlying aspects that are really fundamental pillars that we rely on in order to conduct our studies and our investigations and our R&D. And we rely, of course, on artificial intelligence, on machine learning, on operation research, and also all the evolutions that we see today in networks. We are 150 faculty members involved in this area, in network science and engineering in general, and in networks and IoT in particular. About 500 graduate students, including postdocs, doctoral students, research assistants, and non-permanent staff. And we average about 25 million euros of external funding across the education centers. Now, if you want to look at the proportion in terms of the clustering that we made in the previous slide, basically this is how things are basically partitioned. About an equal, reasonably close weight between network and services and communications, connectivity and physical layer, basically 37 and 40% of the faculty are involved, and then IoT about 20% of the population, and then security and all related issues to networks and IoT are basically around 13% of our faculty and staff are involved in this subtopic. We have about 600 publications per year altogether, and 30% of them are in journals. And maybe now I'm going to describe a couple of major R&D projects that are a sample. This is not an exhaustive presentation of our activities. With 150 faculty members, you can imagine how long this would take. So we are sampling a number of major projects to begin with. These are basically collaborative projects that we're involved in the context on the French recovery plan. Maybe it would be nice to cite the Beyond 5G project that is funded by the French government in the French recovery plan. It's about 10 million euros. It involves a number of key industrial and large groups involved, and also a few SMEs. And our respective education and research centers, and these are the ones mostly involved in there. IMT Atlantique, IMT Nord-Europe, Télécom Paris, but we have also Institut Télécom involved and shown here. And then we have Thales Ericsson involved in this project. And basically we're looking at autonomy and independence in 5G and future networks on general basis. And the objective is to produce harness solutions and technologies at access and core levels, including all the associated and fully independent control, management, and secure architectures and planes. So this is what really the objective is, but basically it's looking at the sovereignty and independence aspects of 5G technology at the national level and the European level. We have also what we call the important project of common European interests that are ongoing now and are being launched. A number of calls are ongoing, so we're working on one on electronics and connectivity. We have also a national program on exploratory research and experimental facilities, basically, and IMT is one of the 3 core leading institutions tasked to really lead and manage this this 5G project on future technologies and telecommunication, and it's funded. The funding level is 65 million euros to do that at the national level. And we are involved in several other joint actions in the context of the recovery plan in 5 and 6G framework. There are projects on health, on multi-sectoral federation, and other projects that we cannot cite more precisely here. I'm going to move on now to selected non-exhaustive research activities and project collaborations. A few selected joint labs. So we have the CEDO lab basically looking at slicing and orchestration right now, but looking at 5G and networks in cooperation with EDF, Électricité de France, that basically is the national energy company. And this involves Télécom SudParis, Mines-Télécom as well as Télécom Paris. This is a joint lab between Télécom Paris and EDF, We have another joint lab with an SME called Davidson or Télécom SudParis, and we are looking at how you can use AI and dynamic modeling for future flexible networks. We have also the Links lab that involves a number of key renowned institutions in France, basically INRIA, Paris 6, Nokia and ERT Systemics are really the key members with Mines-Télécom and Télécom Paris in particular. And they're looking at future information and communication networks in general and covering about the same things we're doing in the thematic area. We have also another common lab in cooperation with Airbus. And in that case, we're looking at how to develop an intelligent control plane to control the network and dynamically configure it. We have also another joint lab. You cannot hear me? Yeah, that's why it's too far from my mouth, and therefore you cannot hear me. Sorry about that. I4C is basically an interoperability for clouds. In clouds today, you have a lot of interoperability issues and incompatible systems, and you have portability and lock-in problems, and we are addressing these problems jointly with a company in order to basically eliminate lock-in and ensure portability more easily. Continuing on really private-public partnerships at Institut Mines-Télécom and in the context of this networks and IoT thematic area. We have industrial partners, the typical ones that are listed here, but I don't think I'm going to cite them one by one. You can see it on the slide. In terms of platforms, I think maybe two interesting platforms to describe are these future industries pilots, which are IMT Factory and DWI that are in Mines-Saint-Étienne, where you have a full Industry 4.0 environment with all the associated technologies, including augmented reality, virtual reality, mixed reality aspects, as they could be useful in industrial environments. And DWI is basically an experimental industry 4.0 product line in order to basically come up with new solutions and both network and IoT solutions for the industry of the future. The LISP lab is basically the internet of the future, where you try to replace basically or you try to separate basically the host from the identities. Silex is an initiative on future IoT and networks at the national level involving multiple institutions. SDR 5G is another platform on software-defined radio for 5G. And there is also an experimental cloud platform available in one of our sites. So this is to really show you the extent of the typical experimental facilities that we have at Institut Mines-Télécom. I am going to continue with some selected platform. This is work done at Télécom Paris. Basically, what you have here is a near field really measurement system called StarLab that allows you to assess basically the effect of propagation and waves on the human body. For instance, what are the effects of the propagation on of a mobile telephone on the head of a person, for instance? And basically, they develop mathematical and experimental methods for that. What you have on the left side, I think you cannot see this. Can I do this? How can I point into the? Okay, on the upper right corner, you have basically the effect of the radiation on the human head on near field measurement. because typically you have far field measurements with anechoic chambers, but you need to do also near field measurements in order to study the propagation around basically the human body, and also in indoor and in proximity and in environments in the vicinity of the users, and the impact of the propagation on the human body and on the people and the environment. So basically, this is work done by Jovia, who's developing dosimetry tools in order to develop anatomic models, create ghosts that can be used to do simulation, emulation, and also using these near field measurement systems in order to assess the impact of the waves on the human body. And this is an example on the image on the left at the bottom is basically the result of the propagation on the human body and the effect of a transmitter that is located in front of the person, and what are the levels of radiation that the human body actually experiences due to these radiations. This is another experimental platform for radio networks, and it's in the ISM band, and of course it targets most of the technologies in the ISM band, including long range and low power communications, and cellular. There is also a cellular experimentation room as well. And basically this is a Faraday cage that is being used to make the experimental analysis of the communication in these various networks. And the cellular experimentation room covers basically from 2G to 5G, including narrowband IoT. And then there are a number of remote basically servers in the cloud that are basically doing the more in-depth analysis, what have you, based on cloud services and cloud applications. So I'm going to continue with some selected activities in the various education centers of Institut Mines-Télécom. This is a set of examples of what is being done really at Télécom Paris, where they're designing antenna in the millimeter range around the 100 gigahertz band in order to create beams that are very narrow at these frequencies, in order to have inter-building communication, for instance, at a high rate. And this is what they are capable of developing, and they have produced recently this kind of beams, and generated this kind of antenna patterns with a very narrow beam width to do so. In the IoT context, they have an on-body sensor network that is being used in order to study the influence of the human body on the communication between the various devices. So the influence of the indoor environment on the body area network is being looked at. And the goal is to do statistical modeling by combining measurements with full-wave electromagnetic and ray tracing simulations in order to assess really the impact of the surrounding, the body on the surrounding environment, and of the surrounding environment on the communication on the smart band or the body area network. This is work done in quantum technologies, networks and quantum technologies, and the goal here is to integrate quantum technologies and quantum cryptography in existing networks that are using, of course, optical communications and more traditional telecommunication networks. This is cooperation between University of California, Santa Barbara and Télécom Paris. Basically, the quantum sources are designed at UCSB, but they are characterized, analyzed, modeled, and represented and studied in terms of performance and in terms of efficiency and in terms of characterization at Télécom Paris. And these are very appropriate for a long-range communication with very narrow beam width, and also useful in the case of quantum cryptography that we integrate in networks. They have been analyzing the interaction that exists between classical optical communication and quantum communication when you use the same fiber. As you use the same fiber, basically the fact that you have variation in power, you have variation in quality, and the interactions that could happen between the two systems. And it's very important to assess basically the interactions and the impact of any degradation, interference, or variation on the fiber on the quantum cryptography systems. So therefore it allows them to assess the stability of the quantum technology when it's integrated in classical networks. I don't know how much time I have left because I'm not keeping track of time. I don't have the timer. Everything I needed is not with me here. 15, 20 minutes, no more. Yeah, that's what I felt I was facing. Okay, in this case, it's information theory and coding, and the idea is to basically develop, identify, and produce bounds on the performance of caching, and the goal would be to reduce the cost of communication, the contention that you could have in the network, and make the system more efficient. So they have worked on an upper bound on fundamental limits for the caching and local storage of content in caching systems. And you have the state of the art as a reference, and then what the current schemes that I were able to develop. This is an ERC grant work. I think it's Michel Huyghe at Télécom Paris that's doing this work. So she actually came up with the upper bounds on the fundamental limits and proposing results where they're nearing the upper bound using their own schemes. Upper bound derivation for caching is what their outcome is, and the best coding scheme based on polar codes that basically does much better than state of the art and gets near the fundamental limits. MIMO decoding using sphere decoder and neural networks here is basically MIMO decoding is very energy and time consuming task, and basically the idea is to use a new neural network sphere decoder in order to reduce the time it will take to come up with the decoding, and there is an improvement of a factor of 100 here, and the idea is basically to rely on this neural network in order to focus on the zones and the areas in the system where you can actually optimize and accelerate the MIMO decoding. Okay, this is also an ERC grant at Télécom Paris on optical communication, where they propose nonlinear Fourier transform in order to basically improve the quality factor depending upon the power that is injected in the system and in the fiber. And they use single and polar and dual polarization in order to do that. And they have been able to improve compared to OFDM. OFDM here is in blue. And then what they have been able to accomplish is in red. So they have an improvement in both types of polarizations, and proposing methods to actually realize better quality factor in optical communication as opposed to FDM. Again, in optical communication using AI, basically this is a receiver design based on neural network. And the idea is to learn the nonlinear channel using training, and then do the equalization according to what you have learned. And the idea here is to identify the zones where you can focus your learning and focus your decisions and your analysis in order to reproduce the constellation after equalization. You have to regenerate your signal constellation, and you see that basically everything is blurred on the left due to the impairments on the fiber and the variations on the fiber and the effects that you can encounter in this medium. And then with the neural network, you basically learn how to recover the transmitted signals. And of course, the ground truth is the green dots at the center of each cluster in the constellation. So they have been able to really considerably improve this, despite the fact that the nonlinear channel blurs entirely and the communication end-to-end. At IMT Atlantique, there is really a joint effort to merge a number of facilities, besides everything they do in R&D and innovation. Silex is basically a large-scale and flexible test bed for experimental driven research. This covers from IoT to large data centers, so the full-fledged distributed infrastructure. Samurai is a green data center completely powered by renewable energy. Grid 5000 is a large-scale distributed grid in France that has been there for a long time for cloud and cluster applications in computer science in distributed systems. Seduce is a green data center partially powered by renewable energy, and basically at IMT Atlantique they're making this effort to merge all these infrastructures and get them to cooperate across the country, and they're involved in national initiatives in order to really merge a number of experimental environments in order to address many issues related to networks and the Internet of Things. At the IMT Atlantique also, they are really doing work on satellite communication directly with IoT, and they're focusing on continuous phase modulation to do so. And there are also there is work on coding, where they have to trade off the overhead between the code length, between overhead and code length for short frame transmission, and they're using also some pre-distortion techniques in order to address the channel, in order to improve the satellite communication in DVB systems. They are also working on static context header compression in order to allow basically the use of IP transport protocols and protocols over long range and low power low power systems, something that was really very difficult to achieve. But recently, by working on 3 dimensions interoperability between the technologies and the devices, the security aspects and the energy, they were able to achieve a very efficient context header compression in order to use IP protocols over limited devices and IoT for Sigfox, LoRaWAN, low power 1 and LoRaWAN networks. And basically they have now an RFC that has come out in the standardization at IETF that basically specifies this header compression that allows you to use IP protocols in areas where it was not possible in the past. At IMT Europe, they're looking at robust networks on the one hand, and also resilient networks. They model interference. On the left, basically, they look at how the interference behaves in propagation in wireless networks. And we know for a fact that it's not Gaussian, but it's rather impulsive. And they use a modeling approach that allow you basically to model the dependence in the structure and then use that in order to improve the systems. They are looking also at increasing the number of devices that can be connected in device-to-device communication or in wireless using power domain NOMA and multi-user detection in LoRa, and they were able to, of course, improve the symbol error rate and the number of users that they can accept in the system. They are also looking at how you can have robust networks when confronted with attacks on the SIP protocol, for instance, and they have been able to use generative adversarial networks for detecting anomalies or attacks in the SIP protocol. So they have been able to basically detect these attacks and remediate or mediate these attacks thanks to the GAN that they used in order to detect the anomalies. Also at IMT Europe, looking at resilient networks where you have basically degradation, faults, or impairments in the network, and you have to react to this degradation. So they're looking at it from a coordination standpoint, a connectivity standpoint, and also a resilience in terms of dynamic adaptation to failures or degradation or unavailability of application services or devices. In the case of the coordination, they're looking at new finite block length theoretical bounds that can be actually specified in order then to come up with practical codes for coordination that are nearing these bounds in order to make the network more resilient when you basically have to find alternative paths to ensure your end-to-end communication and select an alternate route or an alternate set of relays or devices that coordinate and cooperate in order to coordinate their end-to-end transmission. In the case of the D2D connectivity, they're looking really at the multi-hop case and looking at how they can characterize and understand how the network percolates in order to basically make the system more resilient to degradation or attacks. In the case of the disaster resilient service function chaining, basically you have placement of service functions on demand, and then if you have multiple disjoint working paths for this service function chaining, you can optimize the way you use a backup path, the way you reconstruct your paths if there are degradations and what have you, and therefore it's a dynamic adaptation to changes, and you can find a new path where you can find the basically the virtualized network functions that you were using in the path that failed, was degraded, or needed to be replaced, for instance. So they're doing work in that sense. Now at Saint-Étienne, okay, at Saint-Étienne they're really focusing on everything related to efficiency, resilience, and sustainability for the industry, future industries, and for the territories. So they're looking at management, sustainability. They're looking, you have a number of aspects that are addressing for the sustainability and the durability aspects, and they are very multidisciplinary, and they realize that the network is really important, and therefore they're focusing on how they can improve networks and IoT in order to address these key future transitions and transformations in the digital, industrial, and ecological dimension. Since I'm running out of time, I'm going to try to go faster. At Saint-Étienne, they're also working on the semantic interoperability in future industry contexts, but this applies to many interoperability problems that we are facing in networks in general, and they're looking at ontologies, and they're producing solutions for this interoperability at the semantic level, and they're actively involved in smart applications referenced in SAREF and ETSI Smart Band, where they have pushed in OGC and W3C their solutions and their ontologies and their semantic interoperability solutions. And on the right, you see basically the application areas where they will use their multidisciplinary know-how. Also at Mines de Saint-Étienne, they are also looking at hardware security of integrated systems, objects, and embedded systems. So they characterize them, they model, and work on the protection of these systems. And they have a state-of-the-art experimental facility that enables the study of attacks through fault injection and through observation. They use, of course, AI and machine learning to do so, and they're focusing on cryptography and applying cryptography to vulnerabilities, efficiency, safe and trusted integration in these hardware devices, IoT, and low capabilities devices. I guess for Télécom Paris, Télécom SudParis, sorry, I will only say a few things. We are looking at network and services systems and security at large scale. We are fundamentally network and science, network science and engineering focused. We're looking at problems of sharing, configuration, control, and management of network services and resources. So looking, of course, at resource management, but also infrastructure management and their dynamic adaptation. And we're looking at it from many different facets. And the evolution towards programmable and dynamic infrastructures is what we focus the most on. And of course, we use data and model-driven science in order to do so. We have another team that is more focusing on methods and underlying disciplines to basically analyze a model, represent and optimize and evaluate the performance of networks. And we're combining networks, computer science, and applied math. And these are the typical tools that we all use. Optimization is part of it. Typical modeling or everything related to traffic engineering is also done by this team. And we are using all these different disciplines in order to do so. And you have on the right the typical ongoing research. Maybe we can cite the resource allocation in networks 4, 5, and 6G, and then how we do robust optimization, and how we can also verify, test, and validate, and make formal proofs of the protocols, the services, and applications that are proposed, and the solutions that are proposed. These are a set of priorities for the teams at Télécom SudParis, but I'm going to skip this because then I wouldn't speak of the other centers. This is what they do at Télécom Paris. The RMS group is basically focusing on NOMA resource allocation for joint power and subcarrier allocation problems, which is illustrated on the right, where basically you have a certain number of users that you should accept per subcarrier, and you should allocate the power to them. They have come up with models and modeling and algorithms that can really improve considerably the state of the art. They're looking at network MIMO for mission critical communication, where they are also producing cell clustering solutions for that. They are also focusing on telemetry and automation. So basically they analyze traffic, they characterize the traffic, they can predict to some extent the traffic, and through that analysis enable the dynamic adaptation and automation of the systems. So these are traffic engineering methods where they optimize the network on the basis of what they have actually gathered from the metrology by analyzing and monitoring the infrastructure of the networks. And there is also an important activity on the Open RAN in 5 and 6G, where they are actively involved in scheduling for end-to-end isolation of slices, and also optimal placement, like we do in most of the schools and the education centers anyway. And they're looking at resource allocation in RAN. Now, Institut Télécom, basically they want to predict the fundamental limits and design limits approaching methods and algorithms in order to have basically references of what they can achieve in networks at best, and try to reach these fundamental limits. And their key topics basically in this year has been massive MIMO, robot augmented IoT, RF sensing and localization. They're working on caching and AI-driven resource allocation. Mostly here what they do is that they're trying to not only learn from just the data, by analyzing the data and machine learning, and basically drawing, understanding, and modeling the systems, and then providing solutions. No, they would like also to push this further by learning as you go, learning as you analyze, learning online using deep reinforcement learning approaches and what have you, where you can react as you have concept drifts, as you have variations in basically the stochastic and statistical and variation and behavior of the users, the environment, the propagation environment, but also the systems and the infrastructure themselves. As you know, all of them are becoming more and more dynamic nowadays. When we look at Institut Télécom in Sophia Antipolis, you all very well know the open air interface that they are basically the initiator of, that is very well known, popular, and used now across Europe and in the nation. They're looking at 5G radio access and network virtualization, edge computing, intelligent transport systems, looking at vehicular communication, of course, for autonomous cars and V2X and V2V communication as well. And of course, they're using also machine learning, AI for that, which is definitely important. And they have a 5G outdoor test site deployment ongoing that is basically also used in several European collaborative projects. They're collaborating with INRIA, and they have an integration with the Orange 5G experimental facility in Paris, and they are conducting millimeter wave radio outdoor tests at 26 gigahertz on this outdoor test facility. So this is basically what I wanted to present. I actually took more time than I wanted, I guess, or I was supposed to use. And if you have comments or questions, please don't hesitate. We're here to answer them.
We may go go for one clarification question while Professor Kramer is setting up his presentation.
Okay.
And then you will have time at the coffee break or at lunchtime to interact with Djamal and the colleagues and look at the posters, because many answers may be found in the posters, if I'm not wrong.
Yeah, hopefully the posters will give you more. Hopefully the posters will give you more details, more in-depth understanding of what's really being done. This is nothing else than just an overview, and therefore it's fairly abstract and high level.